Evening. Uh, Today's session we will be discussing about the third week, the course NPTEL course principles and applications of building science. And this week's course majorly dealt with shading devices and use of software to do thermal simulation. And the major portion of these things has been covered in the previous session. Since it's the doubt clearing session. The software oriented classes, they are not covered in this doubt clearing session. You can still ask doubts. Mostly those sessions they were for practical purpose and they won't be covered as a part of your exams or assignments. But the actual theoretical problem solving that you should get to know. And since this week covers only a minor portion of related to shading devices, and also majorly what we will be covering in this doubt clearing session will be acoustics part. uh, like this in this acoustic section we give a small introduction about sound and how sound propagates, and also few indicators which are related to building design design for acoustics. And I'll just show you the and discuss some concepts related to building acoustics, and we'll also discuss few example questions related to assignment. Uh, Today, mostly I think I'll be recording the session, and then it's for reference purpose. Also, I'll be showing you a small web-based software which is very useful, I guess, related to shading design. Like the professor would have showed you last time regarding how to do shading design using Ecotect. Since Ecotect is an discontinuous software now, you can still do shadow analysis and simulations in most of the building energy simulation software. So only thing is you won't get exactly the detailed portions like shadow angle and the shadow mask and so showing it on solar chart. These things you won't be directly seeing, but still you will be able to gain more insight directly related to uh, how the shadow and radiation and also the lighting related uh, details directly on the plan of the building or in three-dimensional model. On a particular work plane, you can work it out whether solar radiation is falling or not. This will be also helpful in terms of daylighting, lighting related things we will discuss further in the next week. As we move further, let us also, since this is a kind of a long weekend situation, seems like people will be on holidays mode. Tomorrow is an holiday, and also I wish everyone a happy Independence Day tomorrow. Let us look further into the presentation. Last class, we were discussing about the thermal performance attributes of various building elements, how they play the role, and how we choose various design elements, and also how the construction assemblies, how they play a part in terms of thermal transfer through via conduction, convection, and radiation. And the last portion was about glazing and shading devices. Glazing and shading devices, they go together, and majorly we have to have this conscious decision. We have to make conscious decision, keeping in mind. I'll always go back, and I wanted to remind you about the importance of climate, understanding the solar geometry, and based on the climate context and the site context, and also the orientation of the wall, what type of opening, what type of glazing system, whether you need solar protection or you don't need to allow solar radiation. These things has to be decided before only, and then further we utilize these material assembly concepts, and you, we design shading devices accordingly based on our need. Because imagine you have a hot and dry climate, and then the main idea or aim that you will look for is to try to reduce. uh, Good evening, Philip. Thanks for joining. Today, mostly in this session, we will be covering few shading device related queries, and also assignment discussion will be on acoustics majorly, because two classes out of the five, they were on demonstration of softwares, and the softwares mostly are for understanding purpose and practical purpose, how we apply these concepts further. Most of the cases, the, there won't be any questions related to the software, but mostly on the concepts in the assignment. Since this is an assignment related discussion, I'll just show you assignment related content only. So this will be a shorter version than previous weeks. And also I will try to show you a web-based application uh, for designing solar shading also, which is more easier, because the ecotech, you should have the proprietary software, and it's also discontinued now. uh, if you are not able to access ecotech, you can use this uh, daylighting analysis web tool, and practice and try to have gain more understanding. That is, this is truly practical uh, purpose. Next one, the design builder. Anyway, I think design builder is still available. You can, if you want to practice, you can just download a trial version for 30 days. They will give, I guess, based on the this. Once you register with your email, you can get the software, try it out. Also, like any open source software like Energy Plus along with Open Studio, that is also will work, and look into those further. But this subject, if you are looking into assignment and exam perspective, uh, those softwares and how you apply those softwares, they won't be covered for assignments and the exams. But still, since it's just a doubt clearing session, I just wanted to try to give more, try to share more things related to the application day. But so previously we were discussing about design of glazing systems and also shading devices. When you look into like week two, and week three continued to how do you design shading devices. Uh, And when you design shading devices, it has to be an holistic decision. We have to go into this stage only when we decide according to the climate and the solar geometric, these two context. We have to have a decision that okay, for this site, for this context, for this particular room, I need larger opening or smaller opening. I need uh, double glazed protection, and do I need solar radiation inside my space? Example, for composite climate, it is good to have solar radiation during the cold time periods, but during summer seasons, majorly we try to avoid solar radiation, direct solar radiation. So, design of the shading device for the glazing system is critical, and it has to be looked upon in detail. Uh, so, this solar heat gain coefficient, it gives an indicator along with not just the glazing, along with the shading device also it gives an indicator, because if you have a proper shading device which protects you from solar radiation directly falling onto the glazing, you will still end up with almost like zero point 0.2, zero point 0.1 uh, SHGC. We, even though if you have a single clear glass, because shading also is included in this SHGC calculation, but mostly in exams it will be just related to glazing, and it will be more simpler manner than the practical cases. And for the last class, we saw this also uh, about shading device and shadow angles, how we find them. Like to decide upon vertical shading device, we need the horizontal shadow angle, and vice versa. For deciding the horizontal shading device dimension, we need vertical shadow angle. These formulas we discussed in the last class. And when you see this protractor, this is solar protector, shading mask protractor, they call it. So based on the shadow shading device, there will be a this patch of dark shading. Whatever area is darkly shaded, it means that that particular angles, when sun is arriving, you won't have any solar radiation that is passing through the window to the inside room. So it means that when you look at this segmental mask of the right side diagram of the when you look into like third row, you have this horizontal shading device and the corresponding shading mask. You can see that if you have a particular width of a window till a particular sun altitude angle, you can protect the window from direct solar radiation throughout the day. But at a lower solar altitude angle, you will have direct solar radiation. So for composite climate, if you just provide a nominal width shading device, like around like 0.6, 0.75 width of the shading device, if you provide that, you will be definitely protecting the windows from the direct solar radiation during summer time periods, because the altitude angles will be steeper, and during the uh, winter times it will be coming at a lower angle. So that time you can utilize the solar radiation if you need. And also when you see this lower time periods, like during evening or early mornings, the sun will be coming at a very steep angle than noon or afternoons. So at that time period, the vertical shadow shading device will also play a critical role. Mostly in general, when you see most people provide horizontal shading device and leave it, but the combination of vertical shading device and horizontal shading device, it has to be taken into account. me just stop sharing the screen and again I'll share back eh, the one. Also, let us put the Mangalore. I have loaded a Mangalore weather file. This this is Andrew Marsh. If you just type Andrew Marsh in Google search and then you go to this daylight box uh, section, like share the window, the whole window. I hope you can. Yeah. This is AndrewMash.com. Basically, this person he was one of the major back and behind creation of Ecotech and other energy analysis related software. So he has his own personal website, which on which he has created multiple smaller tools. Like you can also do. Last time I showed about weather analysis, how to see weather data in the three-dimensional charts. In the same way, there are like multiple tools related to solar radiation and also this dynamic daylighting. Like this daylighting, lighting related part we will cover in the next week, but daylighting goes along with solar radiation also. So I'll just try to show that in this uh, session. I'll just try to rush through. I hope this will be helpful for you also. So one thing is shading device. Another thing is we mostly design buildings according to the site context. Imagine in this case, I just thrown few blocks around. Imagine this is our site that we are going to design, and based on the uh, surrounding buildings, we will have certain shadow effect in for the particular site. So we provide a huge window, and then on the east west southeast side here you can see. I hope you can see the name nomenclature of each direction. Yeah, you can see. Uh, this southeast side you can see there is a tall building, and then on this side if you just provide a window, obviously you won't get much solar radiation at all throughout the year. As you see, let me just simultaneously you can just try this out. You can just open your browser and then look into it. I wanted to showcase this because it will be more uh, helpful if you just try to do side by side, or like you can just try. It's more easily accessible. Just open the browser and then you can click. Within few seconds you will be able to get this. And if you want to check what is this shadowing thing for different time periods, you want to think, okay, how the shadow will play out in summer period. Let me just go to some June period. Here June mostly it's, as we see, the sun gets more steeper, but majorly you can see what is this. Yeah, under location actually I didn't select the location. Let me just, here on the left side, the location panel, you go to this location tab, you can set particular latitude and longitude. Let us see here for Delhi, and it will be about this. Longitude doesn't matter. Mostly it's about just the time, what time we keep, that only matters. So we don't have to worry about. Imagine, as I told, the actual time of India's time zone was based on this longitude 82.3. So here you can see. Let me just orient it. Mostly the sun, most time period according to this location point, it is coming almost towards the north, but it doesn't go on the northern side. It mostly comes from the south only. But during the summer time period, it almost reaches the zenith. Zenith is something like you stand and then directly above you, you will have sun over your head. There are some critical particular dates. On particular dates you will get that type of direct alignment of sun where you won't see any shadow at all. Like if you have a if you put up a pole, you won't have shadow around also. That kind of day also we will get. So going back to this tool, imagine like there is a site nearby. You will be able to get this mapping of shadows. So till what particular angle and how much radius, like how much time period. Like here you can see from here during the summers you do get sun from the south east direction because the sun is at a steeper angle. But when I go to time and date and then I go to months of September and October, from morning 7 till 10, there won't be any radiation that is falling on that particular surface. So this tool can be utilized to have that idea that okay, in this time period we don't have direct solar radiation, or we will get ample solar radiation on this side. And if we don't want solar radiation, we can zone particular spaces in that side of the site, and then we can like in southwest side you can see southwest mostly throughout the year we, there is radiation during the afternoons. Like during afternoons there will be solar radiation. So one thing is at site level, this tool can be used to decide okay, in this site and on these directions till an extent where we have spaces can where you have like points where solar radiation is available. Next tool is you have a room and you have windows provided. And in this case, we can add blocks, but let us imagine that it is an open site and yeah, here similarly here we have to choose the weather file. As of now, I chose Bangalore. Like you can download EPW file from online, and then you can just download it, and then select that file and open it to get this data. This chart below it shows the solar radiation from morning to till evening for a particular day of the particular month. Here we have selected December 8th. On December 8th, what is the solar radiation and this one on that particular day and this time scale you have no, this is also dynamic. So it's like you can literally see at 9:35 there is this dark red patch. Like This is for lighting analysis, but I wanted to show you this. You can have an understanding of solar radiation. So if we have a sharp patch, it means that there is solar radiation, and you can see here one window is big. It has a very low sill, and then it is tall window. But other window, you can see it is more like a ventilator or a light shelf type of. So, and one more thing is this is for particular plane, like how it is falling. If you move the plane accordingly, it will change also. That you have to keep in mind. So usually we for daylighting purpose we measure working plane of like around 0.75 meters, and this is just for solar radiation. We'll just keep the same. Imagine keep it simple, and you can see like during winter times and east morning time period, you get solar radiation in this. But in the evening, only around like after 3 only you'll get solar radiation, and also like after 4:30 and then like in winters the sun radiation won't be harsh also, so it won't make a big factor. And you can introduce few shading devices to gain understanding also. Like here on left side there is this window based icon. If you click it, there are multiple options. Add new window. There are multiple windows already. Let us create another one. uh, Add an external obstruction like this. You can add a block, like there is a building here. Imagine there is one small house nearby your own house, which is of 1 floor height, or it becomes 2 floor height. You can make a block like that. So here you can see accordingly directly you can see there is this radiation getting blocked. This since I change, you can see this patch. Imagine it's an open site. We have to design shading devices accordingly. Let me go to another day during May. Here you can see there are like multiple options to choose time, or you can choose the day. You can also choose site longitude and site latitude. You better not switch it. It will become a bit confusing. If we have loaded a particular weather file, we just work on selecting a day and time. So on May during around like afternoon time period, like 3 and that time period, it becomes a bit harsh. That is like a mild patch of solar radiation. So we can try to look into how to provide a vertical. Does providing a vertical device work out? We can look into it. So I'm trying to see that. So see, since even though if I provided a vertical device, since it's almost like perfectly coming from west direction, unless and until you just create another vertical face of wall partition or something that covers the whole window area, you won't be able to block the solar radiation. So there has been some innovative designs, like they provide vertical plane parallel to the window, and then they provide a gap between the window and that vertical plane, so that you still get light and some air movement, but you will be able to block the whole solar radiation also. Like if I go to some other date, imagine October time period, same time, by providing these vertical devices, you can see there is this change happening. Imagine you provide say, three vertical planes on these windows, you will be able to cut off the radiation. So this thing you can just play this out more easier only. If you are well, like if you are familiar with three-dimensional drawing, how to draw and then use three-dimensional interfaces, it is easier. But if you are not knowing this also, still if you just give some time, you will be able to learn. You use left click, sorry, right click and then hold to pivot the whole plane, and then using left clicks you can just place these elements, and then there is this arrow. You can see these arrows can be used to move and also reduce the dimensions. So here you can see there is a drastic reduction in solar radiation according to this type of window shade design. Really you can see how we can provide shading for each window. Accordingly we can design these things. So this tool is very helpful and then dynamic in nature. It doesn't require to like doesn't take much time to like simulate and then show you the results. Since the web design tool, things are running in backend already, so it's very useful. I hope it will be useful for you, I guess. Next, let us move on to stop sharing. Then I'll just go share. Going back to the presentation. So as of now, we covered things related to deciding and designing shading devices and the shadow angles. Mostly, we are just looking into how to design shading devices to protect or allow solar radiation inside. Next, the class that professor took was on thermal simulation. So, if you want, I can give a demonstration, but otherwise you can also look into various tutorials that is available online also related to building design designer building design builder, sorry, software name is design builder that was used, and there are like multiple softwares and help that is available online also. You can look into that further. Let us look into sound. So in this course, we majorly try to cover three aspects. One is thermal, next is sound and lighting. So mostly we looked into the thermal part because thermal part plays a larger role in terms of energy consumption in buildings. But we should not uh, ignore the other comfort related factors which will be very helpful for the well functioning of the buildings, and it will be comfortable for the users inside the building. And one of the major comfort factor is the acoustic factor, and inside buildings there are multiple sound sources that will be coming, and either from the building or outside the building, both has to be dealt upon. And to know about how sound relates to and how we have to design buildings according to the sound requirement in terms of like if you are having some sound related function, like you want auditorium or a concert hall which requires more sound insulation, and we have to look into avoiding echoes, and also equal experience of like audience should be able to have the same similar experience like throughout the hall. Like it should not be like too loud in one side step junction of the space, and then on the other coordinate of the room you don't get sound at all, or you will receiving echoes. These kind of things we should be avoiding. So that is one side. Another thing is for general productive functioning of a space, when we look into sound perspective, imagine it's an office building. You will be requiring like the occupant or the office worker who is working in the space will be having certain sound noise levels that is acceptable. There will be some thresholds which should not exceed upon. So once like it exceeds a certain level, it will start disturbing the function or the productivity of the occupant who is performing particular action. And all these things will let us look into the basics of sound, try to have some kind of linkages about uh, how sound is formed, and what is the sound source, like how sound source is defined as, and how sound propagates, and how sound reacts if to different materials. Like example, you have a sound and then you put a huge wall between yourself and the other person you want to speak. The wall will be a huge barrier. It will affect the sound propagation. You'll be able to still hear the person on the person on the other side will be able to still hear the voice, but there will be some decrease, the reduction in terms of how loud the voice is the person will be receiving. You can just, for example, you just like uh, speaking directly to a person, and then you just suddenly you keep a note in between yourself and the other person. There will be definitely a different change in the sound propagation. So all these things we kind of try to cover it to get an understanding of sound at source, how we can understand how sound functions, like how sound travels, and what and all can be the hindrances that sound faces to travel. So this, if we have this understanding, we will be able to design, like if you want to provide a noise reduction. Like when we look into noise, it's mostly a noise is perceived to be a noise. It's kind of more subjective manner, because upon one person's music might be another person's noise. That is one side, but still, in general, we can categorize noise according to their sound levels. Uh, like there are some sound sources, and that particular sound source at a, if it have some kind of intensity level, like uh, how loud it is, based on that we perceive noise. Like imagine suddenly uh, you are in office space, and then from outside there is a truck honking. You will be definitely getting disturbed. But if you are driving on the road, if there is an honk, you won't mind much, because that is a different context, this is a different context. So that is there. Like also, if you are in the office building and then suddenly there is a construction that is happening next to your site, and then the people are using breakers to break things down, so that will produce a large amount of sound level, which is very irritable to us. So these and are like examples I want to show. So when you speak about sound, sound needs a medium to propagate, because if you, it is a vacuum space, sound cannot propagate. So in space we won't be able to speak to each other, we won't be able to hear each other if someone on the other side is speaking. So, fortunately, we have air around us which act as the main medium. Mostly, when we speak about sound, we air propagates via air only. There are like sound can still propagate through metals or like water or multiple mediums. Only thing is it depends upon their density and well density and temperature of the medium. And here this is the formula. And generally we measure sound using sound pressure level. And this is a mostly easier way for us to get an understanding or like have a small range of numbers we can refer to. But actually the sounds range is very pretty wide, and it is very hard to like imagine, like you cannot speak in terms of like from 0 till 10 to the power 6. At that level we cannot linearly increase and compare. So we use sound pressure level, which is a logarithmic form of sound representation, sound pressures representation. So for that, like we always speak, you can speak sound pressure levels in numbers like, okay, the decibels are sound current sound source decibel is 80, 80, 50, 60. So it is very easy. So for that purpose only we use this sound pressure level, and the unit is decibels. And you can see left in this chart, left side is actually sound pressure. Sound pressure is actually measured in pascals, and as you see it varies from, for uh, human he can perceive sound in this huge spectrum of uh, ranges. So you can see it's like 0.0001, like 10 to the power minus 5, 0.2 into 10 to the power minus 5 pascals. A person can hear the sound, and it can, the same person he can hear the same sound at 100 pascal also, to, from 10 to the power minus 5 till 100. So the difference is like 10 to the power 7. That much range sound level people are able to perceive. So to refer it on a very smaller range which is more usable, we use sound pressure level, and this is calculated using this formula. LP is equal to 20 log P by P naught, and P naught is the threshold value of the sound which is perceivable by a human, like, and this is at a particular frequency. One more thing is main important thing about sound is the sound pressure level that we are speaking, it is for a particular sound at a given frequency. Like there are two things that we have to think about. One is the sound pressure level, another one is the frequency that sound is coming at. Depending on the source of the sound, there is a wide band of frequency the sound is coming at. Like imagine you can just look parallelly like so electromagnetic radiation. If you like sun, it emits, or like some objects they emit a band of wavelength at a particular intensity level. So similar case here, the sound source will produce sound at a band, particular band, frequency band, and accordingly the uh, sound pressure level, it varies. So two things we have to think about when we talk about sound. One is the frequency and the pressure level. And speaking about multiple sound related terms, like these are the four things. One is sound power, which is the source, how much sound power that is emitted from the source, and it is given by this formula. LP is equal to 10 log W by W naught, and W naught is a initial value 10 to the power minus 12 watt. And next is sound intensity, which is measured in watt per meter square. It's more like area weighted sound source type. Next is sound power, which is more like at the receiver side, how much sound power is coming. And sorry, not power, pressure. It, and this formula we saw before only. And last one is the sound exposure, which is calculated based on this formula 10 log E by E naught. And majorly when we look into the relationships between all these things, one is uh, interesting relationship is that relationship between the sound intensity and power. So for a given power of sound, what will be its intensity? Because sound is an omnidirectional source. Imagine it's a omnidirectional source. It its intensity is it depends on the directional component also. Like, so that's why this formula W intensity is equal to watt by 4 pi r square. And so you can see this formula, you try to remember. It's also like, just look into the proportionality, like the intensity reduces with increase in radius. So, and it's an inverse formula, and inverse, so this applies, the inverse square law applies to this sound intensity and radiance. So it means that the intensity of the sound will decrease with increase in the radius of the receiver. The distance between the sound source and the receiver, the distance plays a major role of the intensity of the sound. That we keep in mind, like it will be helpful in solving the assignment questions. Few questions mostly it will be asked in that portion. And next one is the uh, relationship between intensity and power. I is equal to capital P square by rho c. Rho c is the density and velocity. It's usually referred as specific acoustic impedance. And also one more thing is sound pressure is almost more or less, it's kind of analogous to sound intensity. Keep that in mind. And speaking about this inverse square law, what I was speaking before, as you can see, uh, this is that radius, and then this point, dotted line, the dotted point that you see is the sound source. And then according to the distance, the intensity will vary. And in this example, it is shown that there is a 0.005 watt of sound power, and there is a receiver at 2 meter distance. And what will be the sound intensity? This is an example question. Imagine someone is asking you to find sound intensity given that the sound source is power and the receiver's distance from the source has been given. It can be calculated using this formula. I is equal to watt by 4 pi r square. And I is equal, you can see if you just put this problem, it shows that the intensity value is around 10 to the power minus 4 watt per meter square. Sound intensity level at in terms of decibels, how we calculate it, we just take logarithmic form of the calculated sound intensity, and we as we see, this 0.0001 watts per meter square. Once we take log form, it is 80 decibels, which is actually pretty loud for human hearing. And also take a note that the sound level drops by 6 decibels with every doubling of distance. So when you look at sound intensity level or sound pressure level in terms of decibels, the with increase in distance, and if the increase is like doubling, there will be a reduction of 6 decibels. So if it is quadruple, there will be a reduction of 12 decibels. Like that, the sound level keeps decreasing with increase in distance. And also, uh, this there is one common misunderstanding is, you have a sound pressure level of 81 and you have a sound pressure level of 80. These both are not linear difference. It's more of a logarithmic difference. So it means that the uh, there's the difference in like exponent level. Like a larger difference when you say a source is 80 and the other source is 81. So that you have to keep in mind. Um, when you go for like building rating, and then example, for that particular room it has to be rated at 40 decibels. It means that whatever sound that is coming from outside, it should not be above or equal to 40 decibels. It should be below that. And if it is 41, it means that it is increasing logarithmically, not linearly. That we have to keep in mind. Next, another one is, if you have two similar sources and you can try to solve it mathematically, you can see that is this 0.004 plus 0.0004, and if you add both of them, if adjust sound intensity with unit of watts per meter square, you can just add them linearly. But when you take logarithmic form and then try to solve it, you can see the decibel has turned out to be 89 decibels. And in a simplified manner, you can just note it down, and then it's an understanding that if there are two similar sound sources, there will be an increase of 3 decibels. So imagine there are like 200 decibel sound sources. It means that the receiver will hear a sound pressure level of 103 decibel. So whatever it is, like if it is like 30, it will increase by 3 only. So that you can note it down for easier conversion. So this is one example. Imagine we have one single room and then there are like multiple sound sources. There is an alarm clock, there is an electric shaver, there is a vacuum cleaner, there are two vacuum cleaners, and there is a disposal of garbage which is happening, like some household person in your house, either your mom or someone's husband, they are like throwing garbage into a dustbin box. That will also create a certain level of sound. So these, there are like 4 different sound sources. So what will be the sound intensity of the resultant sources? So one more thing is, if you have two sound sources and one source level is higher than the other one, the resultant will be just that single source which is highest. That only will be taking. But another case here, what we are having is, we have two vacuum cleaners which are having the highest decibel level. But since they are like two similar sound level source, you have to add 3 more decibels because they are similar sounds, and the resultant will be 82 decibels. And you compare it with other sound sources. So here if you compare with the alarm clock level sound source and the shaver sound source, there is a difference of 6 decibels. So there is one more table, like if the difference is pretty low, you can add a small minor fraction of decibel. And there's another table I'll try to show. I don't know whether I have this table. I'll show it in the next class. Maybe. Uh, like if the difference is just 2, you can add 2 decibel, and if the difference is 0, you can add 3 decibel. And if the difference is like more than 6, you can just ignore. Like here, if there are like difference of like +9, you can just ignore and take the which is the highest one. You just take them. So that's what you can happening. So alarm clock and shower, they are yielding a resultant of 64 decibel, and you compare it with the vacuum. Vacuum is having the higher decibel, and also if you compare it with the garbage disposal, even that is the same only. Like it is vacuum is having the highest sound pressure level. So the resultant sound level will be mostly the sound which is received by the vacuum. It means like practically what you see is like the sound that you, it's like imagine a person in your home is switching on the TV and then keeping the TV's volume at the highest, and then they are hearing the song. What will happen is, if there is some person speaking and in the background, you won't be able to the hearing what that person is speaking at all. The actual TV sound will be only you will be able to receive. So that's how sound functions. It's not additive thing, it's more like which is having the highest will take a lead. So next one, when we talk about sound criteria, like this one is like at sound, there are like multiple sources, and also sound levels also depend at different time periods also. So there is this concept of L equivalent, is time integrated linear equivalent sound pressure level. What it indicates is over the time period, what will be the time weighted, uh, like time integrated, sorry, not weighted, integrated sound level. And example, in this there is this L10, L50, L90 also, which is basically the sound pressure level exceeding 10% of the time, or 50% of the time, or 90% of the time. What is the sound pressure level? Like L10 is actually, it's like kind of peaks. Like here in this right side, you can see it's like, imagine it's like over time what is the sound intensity level that is being indicated. Imagine in that case, like for only 10 portion you will receive it, it kind of shows the topmost highest level of sound levels, because 10% only means like very short period. What is the sound level? Because when you look into 90, it means that throughout 90% of the time you have that particular sound level. So it will be of lower sound level. 10% means which are at higher for that given sound situation. So L10 kind of indicates that okay, there is like sudden spikes. If you have like in a room, there is someone suddenly starting an water motor, that kind of gives a sudden spike in sound level. So this will be kind of an indicator that okay, for L10 is 90, imagine. So you can take the indicator that okay, L10 is 90 decibel, and then L90 is around 30. It means like it remains quiet for most time period. It means that L90 means that example, if L90 is below 20, 30 decibel, it means that it remains quiet for that long period of time, and mostly this higher level of sound pressure levels are for only short period. So this L equivalent values gives an indicator, and try to remember this. L equivalent is time integrated linear equivalent sound pressure level. And Okay, two things. There are a few formulas which you can look into. One is sound pressure difference between 2 points. You have like two different points, and then they are at different distances from the actual receiver source. And to find that difference, you have can use this formula to find the difference. Another one is we have discussed already that based on the directional source, it's similar to that sound intensity and wattage relationship. Only thing is we included this directivity part also. Like before intensity and watt relationship, what it is I is equal to watt per 4 pi r square. Now in this, including the direction source, I naught is equal to I theta is equal to watt into q by 4 pi r square, and q is the directivity. And this directivity part here, this q value you can see, if you have an omnidirectional sound source, which means that there is no obstruction around that whole sound source, like not above, not below, not in front, back, or sides. You don't have any obstruction. This is more like if sound source is in a space, or it's like at a higher point. And next one is a general case. You are in an open ground, then you shout. It's kind of similar to the second diagram, which is you have a plane, and then in this, the q value, the directivity part, it becomes 2, which means that the sound gets reflected from the horizontal plane, and it will again will kind of like you have one sound source that is directly, you have one receiver in front of you, not like just next to you. It's like imagine the receiver is at like some 3 meter distance level. So one sound source directly that the receiver will receive is directly straight, linearly it will travel from your side to directly to the receiver side. But there will also be another sound level which is resultant of the reflection from the horizontal surface. Like it's like the sound will go hit at a at the horizontal plane at an angle, and then it gets reflected, and then the receiver receives it. So that is how this Q, the directivity concept plays. Like with increase of planes, multiple. Like if you have very short, small room, the so if you speak at a particular sound level, the receiver will be able to receive it very effectively in a small room. Imagine like in a closed small room, the sound is very much amplified. The best example is in generally in you come across this bathroom singing concept. People start singing, they will be able to hear themselves very easily because you are in a very small space, and then it gets reflected, and then you will be receiving the sound level in a more amplified manner. So, and that's how, like if there are like one single plane, the directivity is 2, and the next, if you have two planes, the directivity becomes 4, which results in increase of 6 decibels. Like you can see, the with increase in number of planes, there is an increase in the decibel value also. So here, if you have a corner, like in a three-dimensional manner, if you are like the sound force is at a corner, and then there are like three planes at different coordinates, cardinal direction. So it will result in Q of 8, and then there is an increase in 9 decibel values. So that you can keep in mind. So in this, from a microphone, there is an sound source of 86 decibel base, and if you have the same sound source having three different planes, like the bottom portion what it's seen, the resultant sound will be 95 decibel, which is an increase of 9 decibels. This directly keep in mind, like this question also keeps coming. And next, previously I had mentioned about sound source and the other part, which is the frequency associated with the sound source. So we have there will be a band of sound source with some band of frequency also. Here you can see in the last bottommost graph, like a tuning fork, it provides sounds pressure level at a particular frequency. So you will receive only one single, like at a particular frequency level, you will receive that loud sound. Like it's like your tuning fork, you hit it light, you will still receive at the same particular frequency, you will receive a very less sound pressure level. It means that you won't receive that sound much. But if you hit it hard, it gives more higher sound pressure level, but at the same frequency. So that's how it is. And if you have an instrumental music instrumental device, it will have high frequency at sorry, has high pressure level at a particular frequency, and it kind of like have another set of frequencies, but with lower sound pressure level. And if you have a complex sound source like a ventilator or a fan motor operating, there will be like multiple parts that is generating the sound. It kind of becomes a huge chaotic mix of frequencies, and then you'll have a complex range of frequencies, but there will be some higher frequency levels. Like for that particular frequency, there will be higher sound pressure levels. So there will be it will be a band, like this, that we have to keep in mind, because we have to design buildings with what is the sound source that we are dealing with, that we have to keep in mind, and accordingly we have to choose the design and the materials also, because multiple materials will have noise reduction capacity at different the frequencies. Like it's like if you have a perforated board, it might be very effective protecting sound at high frequencies, and it might be for another type of manufacturer, it might be reducing, might be capable of reducing the sound at lower frequencies. So these combinations we have to keep in mind. And this speaking about noise barriers, it depends on the width and depth of it. And generally, when we speak about noise, we can like we cannot like keep too much things in detail. Like can think as consultant how things function, but for providing standards or generalized normal understanding, we kind of use some generalized forms. Like here you can see this graph, what it shows is different noise criteria for particular usage of the building. Example here, if you have like each indicator, like here the topmost portion, it is the noise level of a very loud stereo playing in living room, and you have another next below one, it is air conditioner humming in the living room. So these are specific sound levels, and at particular frequency you can see the marking. There is an x-axis and also y-axis. The x-axis defines the frequency, and the sound pressure level is indicated on the y-axis. And this noise criteria, like example offices, they might have noise criteria of 40, which means that we should try to have the noise level reduced below that level. We have to try to maintain it. So noise criteria, though we have multiple spectrum of sounds, we try to push it down at particular noise criteria level. And this curved gray shaded line, curved line you can see is like, even though there is a high amplitude of or high sound pressure level for lower frequencies, they kind of gradually go down. It means that like for higher frequency, and lower, with increase in frequency, the loudness matters a lot. Like the sound pressure level matters a lot. Next one, the concept related to sound propagation is this: how sound whatever it is, no, the sound will start propagating and then it will die off. It means that it won't be producing any effective uh, reflection, and it will die off means uh, at that threshold it will go below the threshold level of hearing only. So here you can see it's like if you have an omnidirectional point source and then you have this cubical volume surrounding the point source, the sound gets reflected and it may die out in after 16 milliseconds, depending on the sound intensity level and also the dimension, and also the how far each plane's distances are. So these things you just have to remember. Next one is the concept of reverberation time. This is basically to find how much time it will take depending on the surface and also surface property, how much time it takes to die out only. It's not it's kind of a time component, and it is using, you can calculate it using this formula: TR is equal to 0.163 V by A. A is the combination of the uh, area and also the surface reflectance value. Next, and this V is actually the volume. Imagine a room of 4 by 4 into 5 meters, and the volume it comes out to be 8, and then there are multiple wall coefficient, sound coefficient that has been given according to the wall, and also we can try to find out the wall area and also multiply it with uh, the wall sound coefficients, and we try to equate it and then find this A1, A2, A3. Once we find it, we add everything together, and the reverberation time we can find, and then it is giving out the value is coming out around 0.228. This is one of the usual assignment questions based on you will be provided with this wall coefficients and dimension of the room, and then you will be asked to find the reverberation time. This reverberation time concept is basically critical because in auditoriums and all, if you have a musical event, you don't want the sound to die out very soon, because music you perceive it to be pleasant if it resonates. But if you have a conference room type of thing, you should, if you want to have a clear conversation, you should have very low reverberation time. That is also important. These things we can look into the next class also. uh, not covered, we can just look into. Next one thing is like speaking of noise barrier and noise control, we have to look into this actual materials related to noise, how we control noise using noise barriers, and there are multiple types. One of these is this porous absorbers. It might be like vertical or horizontal. It might be sticked along with the surfaces, or it can be suspended. There are multiple types of noise barriers. Uh, these are not like structural elements. It's more like acoustical treatment that go along. Can also integrate it uh, in the earlier building design stages only to give more holistic solution than like you design a room and then you decide that okay, I want to convert it into an auditorium. Instead of going that, if you include the design in earlier stages, it will give you more of an efficient solution. And see here also you can see the absorption coefficient value, it varies with the range of frequencies. Here you can see these panel observers, they are very effective at lower frequencies, but not so in higher frequencies. Uh, that's uh, on the left side, that graph what you see, it's like if the absorbance coefficient is 1, it means it's a perfect absorber almost, and if it is going near 0, it means that it is not so effective in absorbing. It's like sound like will act as an X-ray at higher frequency. It just pass along the material. It will the other person on the other side. It is able people will be able to hear, or if there is a wall, it means that it will go through the porous material and it will hit the wall, and then it will get reflected back also, which might lead to echoes, like, or some kind of echoes are basically like you have a intended sound source which will take some time. It will be happen in like millisecond time duration. A receiver will be able to receive it at a particular distance. He will be able to, he or she will be able to receive it at like a fraction of second. But because of this reflection component, there is a small same sound which was uh, released before only, and the receiver received the same sound after a small gap of receiving it directly from the source. So there will be like similar sound that is with just one single point. Like if someone shouted you will receive the same again and again over multiple fractional time periods. So that is a defect. So we have to decide what type of shape. Like we are not discussing here the shape, but morely when you look into this sound noise barriers, we have to choose materials accordingly depending on the sound source and the sound source's frequency. Here there are this list of table shows us various uh, sound proofing materials. Some are like common materials also. Here this concrete terrazzo masonry. It is a very poor sound noise barrier at multiple frequencies, like ranging from 125 hertz till 4000 hertz. Generally, this NRC value is an average of sound absorption coefficient for 250, 500, 1000, and 4000. That's how it is calculated. And here this is almost zero. And when you talk about gypsum board, gypsum board functions well at lower frequencies, but not so at higher frequencies, that we can see. And imagine we have this carpet. It is a very good solution for higher frequency, but not so at lower frequencies. Then we look into this observers like puff boards, soft porous puff boards. Here you can see they have value of zero point 0.4. It is modest at lower frequencies like 0.05, 0.15, 0.25, but at higher frequencies of like 2000 and 4000, you can see it's almost 1. It's almost a perfect absorber. Means that it will absorb high frequency sounds but not low frequency sounds. And let me stop here. Let us go into few example questions. Uh, Try to guess now. If you are not able to guess, I'll just give a pass, then I'll just show you the answer, and then I try to explain why it's happening. Uh, Vertical shadow angle is associated with which one? Here, basically, when I showed vertical shadow angle and horizontal shadow angle, these things play a role in designing the shading device. And when you talk about vertical shadow angle, it means it is dealing with horizontal shading device. and vice versa. If we talk about horizontal shadow angle, it deals with vertical shading. It's kind of a vice versa thing that you have to keep in mind. Here the answer is horizontal shading device. Next one, in a solar chart, the radial lines, what it represents. Speaking of solar chart, I hope you remember the chart. Let me go to. Yeah, I don't have the. Okay, this protractor, it almost shows the same thing only. The thing is, even this has solar chart. Here, these radial lines, what they show, and there will be concentric circles. What they show that have to keep in mind. Here, the radial lines actually show azimuth angle, which is like from the plane horizontally how many degrees the sun is located from on an horizontal plane. It's totally looking into horizontal plane. Just you see from a top view and looking into the ground at the plan level, you are like literally marking sun's point on plan level, and then next one is you have one plane, sorry, one line, and then and you put a perpendicular line to that plane, and that from the angle between the sun's point and the plane perpendicular line, that is the azimuth angle, and these angles are indicated on the radial lines of the solar chart. And there are concentric circles which shows the altitude angle. These things I remember. And yeah, in acoustics, you try to remember what are all the sound terms and what is the associated unit, and and also check it for the same particular sound property, what is the SI unit and the colloquial unit. That also you try to remember. In this question, it is asked what is the sound pressure level measured in what unit. So sound pressure level, it is measured in decibels, as we discussed. But when we talk about sound pressure, it is measured in Pascal. When we talk about sound power, we measure in watts. And the hertz is the property of frequency. So the unit of frequency. You know that. And in this is more like a practical example thing, like what happens in naturally compared to a male voice. The typical female voice has slightly predominance of what? What is the question? Like, is there a difference between male's voice and a female's voice in terms of like frequency? You guess. So basically, compared to male voice, females uh, they have but higher frequency. So male, they will have usually they produce sound at lower frequency. It's not the difference of loudness; it's mostly difference of frequency the sound is coming out from. So that please uh, remember it. Next one is what is the linear unit of loudness? So loudness is mostly a subjective term, you can say, but there are also loudness which are people they define in terms of multiple ways. Uh, there is one way of uh, measuring loud, like depicting loudness. One is at linear and also normal level also. On a linear unit, loudness is spoken as in terms of tones. So linear unit is sounds. It's not general unit. Linear unit is sounds. Next one, two similar sound sources. This you try to solve it. Longer form is trying solving it using that formula. I is equal to quad pi 4 pi square, and then when you have this radius and power related thing, but here you have just two similar sound sources based on the intensity and the sound pressure level relationship. We can try solving that, but as we spoke in the previous like few minutes back, when we discussed it, is that when you have two similar sound sources which are of equal sound pressure level, if the resultant sound pressure level increases by 3 decibels. So which means that in this case, the 66 two sound sources will result in a sound pressure level of 69 decibels. Next, in this case, we have two sound sources with pressure level of sound pressure level of 101 decibel and 110 decibel. When they both produce sound at the same time, what is the resultant sound pressure level? This is the question, and this is also, as I discussed earlier, if there is a significant difference above like 9 decibel or so, it means that the higher decibel sound will take the prominence, and it will, only the higher resultant sound we have to take into account. It won't provide any average sound, or it will not add up to and provide some 121. The result sound will be the higher one, which is 110 decibel. But if you have similar sound sources, it will same case. You just add 3 more decibels, it will become 113 decibel. Next question: in unobstructed outdoor environments, the sound pressure level of a non-directional sound source reduces with quadruple of distance. This is basically question related to the inverse square law case only. So with every doubling of distance, the sound source will reduce by 6 decibels. In this case, the sound source has the distance has increased by quadruple. So with quadruple increase of distance, the sound source pressure level will reduce by 12 decibels, because it doubled, there is a reduction of 6, and again it doubled, it means there is a reduction of another 6. That's 12 decibels. Next, the sound attenuation of noise barrier is associated with. So attenuation, it deals with multiple factors. One is personal number, another is frequency, and also the height of the barrier. So all these three, they kind of play a role in sound attenuation. Next one, the term rumble in a room criteria curve is associated with what? So rumble is mostly associated with low frequency sounds. So it's most like if a group of people, you can imagine, say, the concept of like speaking what is there a difference in frequency between male and female guys. Male, they are found to have lower frequency sound. So similarly in this case, like generally lower frequency sounds are that. In the previous case, what I told is like comparatively they speak at lower tone, doesn't mean that they speak at very lowest frequency band, and female voice comes out at higher frequency band. And try finding out what is the frequency band of male and female, if you are interested. Here, generally, lower frequency sounds get a curve is associated with the term rumble. So, with that, I'll just stop this presentation. Uh, as of now, this week we wanted to cover sound and shading devices, and also uh, thermal simulations. It's not covered as part of the sound clearing session in terms of assignment. What I'm speaking of. You can ask any doubts if you have anything. Uh, I'll just stop sharing the screen. Uh, Thanks for joining. If you have any doubts, actually, this session is supposed to be interactive session, uh, but still we try to also like provide some kind of run through so that people are not people are reluctant to ask doubts, or like they don't still don't have doubts, but they just want to have some additional information. I try to provide that. So hope this was useful for, and next week it will be the last doubt clearing session. I think before the exams also there will be one more session. We'll be just trying to cover all the assignment related questions, and if you have any doubts related to exams, that will also cover. And next week we will be covering about acoustics. Again, few next further details on uh, concepts on acoustics and noise barrier, noise reduction criteria we will discuss. And also we will look into lighting design. Lighting this is also another spectrum where we try to utilize how we can look into like how we utilize daylighting and what multiple aspects that detail about lighting we will look into. Have a good evening and happy Independence Day, everyone. Uh, Thanks for joining. If you don't have doubts, we will close the session. I'll just wait for a minute. Thank you.
Thank you, sir.